Okay, so hello everyone. Welcome to the first virtual time series seminar of the 23-24 edition. It's our great pleasure today to have Alexander Auer from UC Davis, along with our guest panelist Alexei Onatski from Cambridge. And as usual, the seminar is 60 minutes. If you have any questions, please go ahead and ask. And Alex, the floor is yours. Thanks so much for joining us.
Thank you very much, Mashid, for the invitation and the rest of the organizers. It's a pleasure to be here and give this talk on high-dimensional time series and how random matrix theory might play a role in helping to analyze these objects. What I'm talking about today is partly based on some older work with a former PhD student of mine, Hao-Yang Liu, who works now for the Federal Reserve in Dallas, and Debashish Paul, who is my colleague here at UC Davis, and who unfortunately is actually on leave for 1 year because he's back in India to take care a little bit about his parents there. But he should be back here in next summer. So some of this work, as I mentioned, is a little bit older, but it sets the background for the newer stuff that I want to talk about today. And so I'll still explain the old work in some detail because it's important that we have that background to understand the new methods that are coming. Oops, that was too fast. So I spent some time on introducing random matrix theory. For the independent case, I just show, for those of you who are not that familiar with this field of research, what the result is that we mainly want to see generalized to some form of time series case. And I review something on the dependent case that had already been there when we started working on this topic. Part B is, as I mentioned, somehow the older part. So that has been around for a few years. We talk about eigenvalue distributions for sample covariance matrices and symmetrized sample autocovariance matrices for certain linear time series. And I'll try to explain what you have to do to basically lift the independent case results to the time series setup by focusing on the simple MA1 case to highlight what's going on. And then finally, I talk about how these results in part B could be made useful in terms of estimating things that are of interest in application. So for example, we have some theory for estimation of quadratic forms that use these spectral theory results from part B, and I want to apply them to one of the classical problems to estimate the mean variance frontier. And it's known that somehow the risk is often underestimated in empirical situations. And here you can try to do it in a high-dimensional setting. You can try to figure out how to correct that risk underestimation, and you can give even a formula that basically tells you where that underestimation is coming from. And to estimate this mean variance frontier, or more generally quadratic forms, we have tried to establish a thresholding and cross-validation approach to do so. And I'll show you some empirical results in the end that hopefully highlight that this stuff kind of works. Okay, and then I'll conclude. So that's the plan for the next hour, maybe. Okay, so starting slowly with the introduction. So this is just the usual prompt where you're saying that the data has become more complex and we need certain new statistical tools that help you go through these new data analysis challenges. So the applications come from about any field, but here, as I mentioned, we're focusing on something that is more of interest to people in econometrics, perhaps. These high-dimensional phenomena that we want to talk about, they basically invalidate certain classical results that you know from multivariate statistical analysis. And we're talking about new theoretical tools besides applied tools and empirical tools that you have to try to understand in order to address these questions. There's a lot out there. In our case, we want to talk about random matrix theory. And there is literature on this. So the standard book, I guess, has been for a while the Bai and Silverstein Spectral Analysis of Large Dimensional Random Matrices. If you're interested in other types of high-dimensional statistics, then Peter Bühlmann and Sarah van der Reer's book is also maybe a useful resource for that. Okay, so random matrix theory is something that has been moving over from physics into statistics very slowly. If you look at the origins of random matrix theory, it was already there in the 1950s when Wigner realized certain things about heavy atoms and energy levels that could be described by eigenvalues of random matrices in situation when explicit calculations are infeasible. And there were approximations through what's now called the Wigner matrix, I guess, that matched the observations very well. And so it was kind of around in physics and used extensively for a while before it made its way into mainstream applications, I should say, in statistics. So the applications are now everywhere. If you talk about dimension reduction, hypothesis testing, clustering, regression, or covariance estimation, the literature that is around is kind of in these 4 points here. It increases in complexity. So much of the work is on the empirical spectral distribution. That's the part that we have contributed to. And then there is certainly even more complex situations when you talk about the extreme eigenvalues or the distribution of spacings of eigenvalues and the behavior of eigenvectors. All of this is not really part of this talk. We're just staying with empirical spectral distributions for the time being. There's a review paper in JSPI that Debashish wrote kindly with me, I should say. So in a way, when I started to learn about random matrix theory myself, Debashish was asked to write this review paper, and he said, since we're doing this anyway, maybe you should be part of it. And so this is his work, and I somehow made my way onto that paper. So what is this whole random matrix theory situation? What you're trying to do is to do asymptotic slightly different, and you want to take into account that you are talking about a high-dimensional phenomenon in the following way. So you have a data matrix X, P by N, and the dimensionality P of the problem is actually something that's attached to the sample size in a very specific way. Namely, you want the ratio of P and N to go to a constant gamma as N goes to infinity. Okay, making that assumption has certain consequences that we talk about in a minute. But for Wigner matrices, for example, that we talked about before, you would have P equal N, so gamma is equal to 1, and you have certain conditions on the entries of the matrices that talk about the physical system that you want to describe by it. For us, we will talk more about Wishart matrices because they are closely related to the sample covariance matrix that we're, oops, sorry, I have to turn the light back on. UC Davis wants to save money, and if you don't move, they turn the lights off on you. So I'll try to jump around a little bit during the talk, so it won't happen again. So anyway, so these we want to understand this matrix S down there at the bottom, and therefore we try to put it into this RMT framework. All right. And so what we want to do is we want to understand how the eigenvalues of S behave as P and N go to infinity in this specified way. So the first problem that you have is if P and N are growing at the same time, the classical situation that you accumulate degrees of freedom is not happening, right? So relative per entry, you are basically stuck with a fixed degree of freedom. Okay, so how to study this then? If the underlying matrix space even is changing with P and N is one way to do it is to focus on empirical spectral distributions. And if you have a Hermitian matrix, like for the sample covariance matrix, what you can do is you can just look at this function f here that collects the proportion of eigenvalues to the left of a point x. So that's a distribution function. That's one of the fundamental objects in random matrix theory, and it's gonna be useful for us too. So for example, if you want downstream talk about linear spectral statistics, then they can be understood in terms of integrals with respect to the empirical spectral distribution. So understanding what's going on with F is helpful in this case. Okay. Good. So, and just to give an example, in these talks, I often use this n equals 10, p equals 10, not so high dimensional simulation that comes from an Ian Johnston review paper from a while ago. And what Ian did is he used just standard Gaussian random vectors with an identity covariance matrix. So everything is clear in that case. The population eigenvalues are all equal to 1. And you can start to simulate from this. And I did my own simulation run here. You have, you compute S based on your observations, and you compute the 10 eigenvalues of S. And if you do this, then you get something along the following lines where you have one extremely small eigenvalue on the left, and then you have something that is orders of magnitude larger on the right. And if you're not careful, you could say that perhaps the population eigenvalues would be different from another and also different from one. Okay, so the questions that follow is what happens if you increase N and P in the random matrix theory framework? Does it go away? And of course, it should not go away. Otherwise, my talk will not be 1 hour long. So if it doesn't go away, we would like to see what is responsible for this disconnect between population and sample behavior. Okay, and here is the situation for N and P equals 1000. So the aspect ratio P over N is kept the same. And you can see a similar spread, right? So the smallest eigenvalues are very close to 0. There's a pileup out there in that histogram, and then it tapers off so that the largest values are roughly equal to 4. If you decrease the aspect ratio, so P over N becomes 1/2 in this red histogram, this pileup effect around 0 is going away. And the range also shrinks. The largest eigenvalues do not reach 3 now. And you can play that game further. So for aspect ratio equals 1/4, it centers more about where you want to be, namely the population value is 1. And even in a situation when many people would say that's the classical situation, P equals 100 and N equals 1000 perhaps, there's still a significant deviation from the population eigenvalues in this case. Okay. This was understood for a long while, actually. Since the 1960s when Marchenko and Pasteur solved what was going on. And of course, the result now carries their name. Let's assume that these x's that we're observing are all standardized. That means that they are centered. Their second moment is 1 and their fourth moment is finite. Then this empirical spectral distribution, so the distribution function that goes with the histograms that I showed you, can be shown to converge almost surely to a non-random limiting distribution. That limiting distribution has a density because it's continuous, and it has a closed form. So it is, first of all, compactly supported on an interval AB, and then it has this particular square root and so on form. The interesting part about this is that this distribution only depends on a parameter gamma, and this is the limiting aspect ratio. The rest, whatever you had of the observations, just falls out. So for example, we had P over N equals 1, in which case gamma would equal to 1. And you can see that the support of the density goes from 0 to 4, which was kind of what you saw in the histogram. And you can double check these endpoints for the other aspect ratios, and you'll see a very good approximation to that behavior. The first black bullet point here is for gamma less or equal to 1, so you don't have point mass at 0. If gamma is larger than 1, you have to slightly adjust it and then put a point mass at the origin with the corresponding weight. Okay. So you can see that this establishes in the random matrix theory limits the eigenvalues of S, the sample covariance, will spread about those of the population covariance sigma even in the limit. So the fluctuations are not going to go away. That's different from the classical situation. And also, if P over N goes to 0, then you can see that A and B will collapse onto each other. And so the smallest and the largest eigenvalues will both converge to 1. And in some sense, you get the classical results back. Instead of showing you this formula, I should have probably just put the picture up here. So these are the Mashenko-Pastur densities based on these 4 different aspect ratios that we have been talking about before. And you can see that the empirical histograms that I showed you before and those population ones, there's a very good match. And I think that's one of the more surprising things for me when I started to work on random matrix theory is that the finite sample behavior of these eigenvalues is in most situations extremely well matched with those that are predicted by the limiting situation. So I would say that this is a very good argument for why random matrix theory should be very helpful in applications, even though I know, especially maybe in the US, there's some hesitancy for statistics people to work too much with random matrix theory because the technical background is kind of different of what you traditionally learn in the statistics curriculum. So many people have maybe a little bit of hesitancy. So when I talk about random matrix theory, I try to focus on telling people that there is actually quite a bit that can be gained in terms of making better statements about data. Should not be primarily like a mathematical exercise, right? Even though that's also interesting. All right. So that's kind of the background for the independent case that we're trying to exploit when we want to go to high-dimensional time series. So we understand a lot about univariate and multivariate linear time series. We know when ARMA models work well and maybe when they don't work in practice. Moreover, you have tons of extensions, and important for those who want to apply it, you have computer packages. You can just use it without having to worry too much about implementing things on your own. However, these high-dimensional time series, of course, run into the curse of dimensionality as well. The estimation becomes, in full generality, impossible, and you need assumptions on coefficient matrices to make things work. And typically, one of the primary ways to do it has been you impose sparsity somewhere. For high-dimensional time series that try to not impose sparsity, there's very few results in the literature. We're going to give some part of a review in the next couple of slides. And compared to these ARMA univariate, multivariate models, we still are kind of in the beginning of the research on that. Okay, so just let's take a step back again and look at why it might be useful to study this in more detail. So let's look at just standard normal Z's, and we can define two processes from that. We can take an independent one, and we just use the x's to be equal to the z's, and we can just create like a kind of a moving average of two neighboring z's, so like some sort of an MA1 process. And you can compute the covariance matrices that come from both the independent and the dependent process, so as int and as step. And you can plot the eigenvalues that you get from this against each other. So you could do something like this. So even though on average, the expectations for both covariance matrices are the same, that's why this 1/2 sits there to make that equal. When you plot them, you find that they do not line up along the 45-degree line. They line up very differently in a nonlinear way. So there's a nonlinear effect once you go from independent to slightly dependent cases. And we would like to see how we can quantify this time series effect with the methods that we're trying to introduce. Okay, so that's the first goal. So when a time series dependence enters, it's not a simple transformation from the independent case. There is some nonlinearity attached to it. Okay. You can also check the histograms. So for example, here is again S for n equals 2000 and P equals 1000. So aspect ratio 1/2, independent case in this purplish color is what we had before. And then you can do the MA1 case on top of that. That's the MA1 that was described in the previous slide. And what you see is that the histogram somehow stretches out, right? So your largest eigenvalues are now way above 3, and so bigger than predicted by the independent case. So if you ignore time series dependence, even a weak one like that, you are led to wrong conclusions in the sense that maybe you want to say something about signal in a noise and you try to describe your noise behavior by the purple histogram. You're seeing a lot of signals sticking out here, even though that's perfectly normal given that you have a time series rather than an independent process. And you can do that for more complicated dependencies, like here's an MA2, just average 3 of them and divide by 1/3 and compare the histograms, and you can see that more stronger time series dependence would lead to more false discoveries in a way when you base your instincts on independent situation. And that, of course, is something that many people don't really like to hear, right? So they want to make discoveries. This one says basically the opposite. There's nothing to see, right? So that's a thing you have to keep in mind when you talk about that. However, so that's kind of the situation that we're dealing with, and now we would like to understand the theory behind lifting the Marchenko-Pastur kind of to a class of linear time series. And this is in this older paper that I mentioned earlier. So what we want to do is we want to give a description of this linear process in high dimension that we can use to understand and characterize eigenvalues of first sample covariance matrices and then a version of the autocovariance matrices. And I'll say later why we talk about symmetrized versions there. Okay, so before I go there, let's look at what other people have been doing in the literature before. Pfaffel and Schlemm, they were PhD students at Technical University in Munich, working with Claudia Klüppelberg at the time, and Chanfeng Yao from Hong Kong. They pretty much at the same time looked at a similar problem, but what they did is they studied linear time series models row-wise independent. Okay, so basically they have a lot of different time series, but each row of the processes they run independently of each other, and so they can basically say something about the eigenvalues of covariance matrices for this case. Jin et al. this is an annals of applied probability paper from a couple of years after those first papers. So they looked at symmetrized autocovariance matrices and looked at the behavior of those for the independent case, right? So the population autocovariance matrices are all zero, yet the sample autocovariance matrices, they have non-trivial behavior, and those guys in this paper, they figured out what that behavior is. And then maybe the most complex paper is already published in 2005, and it's about a bistationary Gaussian process and more related to maybe spatial temporal processes than the high-dimensional time series situation. And this is a paper by a French group. Okay, so that was the stuff that was out there at the time when we were trying to work on this. So let's look at the simple case of an MA1, not quite as simple as the one before, but something along those lines. Let's look at XT, where we have an MA1 with a coefficient matrix A1 that could be random but independent of the innovations process C. If this is random, then somehow we need an insurance that this A1 doesn't behave too wildly if we're taking it to the limit when n and p go to infinity. So we're making some sort of a regularity condition that the eigenvalues of this matrix are nicely behaved. Okay, so the motivation for these assumptions, if you look at this, we want to say something about the eigenvalues of S, the covariance matrix, sample covariance matrix. For this MA1 process, the expected value of the sample covariance matrix has this expression. When we look at the assumptions that we're doing, we would have to understand polynomials in A1 star, and then the product of those two. But these two conditions, A1 and A2, they allow us to reduce the complexity of the problem, and we only have to figure out something about A1 rather than the whole combination. You could probably use free probability and things like that to weaken these conditions, but we did not try because none of us really understands free probability. So these assumptions are here for clarity, I would say. They are not necessarily the generality that you can go to. And they're certainly not what you would find in practice, right? So they are here to highlight what can be done and what effects you would see. So then what I wrote down here is somehow the spectrum up to normalization of a scalar MA1 process, right? If you look at X as a univariate time series, then this is kind of the spectrum of that. Okay, and then using that spectrum, you can come up with the kernel that reflects the time series dependence in a similar way. And what you need to do is to understand what's going on, you need to understand those average traces in the powers of your MA1 coefficient matrix. And the one for k equals 0 is the one that you're actually after. So it's kind of an involved problem where the one that you want to understand is somehow bunched together with a couple of other things, and you have to disentangle what is going on. And the disentanglement in this kernel somehow respects the time series dependence in the form of the spectrum that shows up in there. Okay. And this is what explains this nonlinearity that you saw in one of the previous pictures. Okay, so here is the actual result. So you can see we want S0, which is S. It has this integral equation, which basically tells you something about how the dependence is distorted or is, oh, here we go again. Sorry about that. The dependence is distorted according to the actual time series dependence that you see, according to a spread out relative to the uniform distribution that you would get from an IID process. But it is also involving this kernel K, which itself is given by an integral equation. So in the end, you have to solve these things numerically to make it applicable to practical situations. But as a theoretical result, it's kind of, I don't know, maybe cute, maybe not. But it's an interesting thing, and it basically tells you how to transform the independent case to the time series case.
Alex, may I ask you a question?
Of course.
I'm sorry to interrupt. So you mentioned a couple of slides ago that in principle one can use free probability theory, right, to figure out what exactly?
Yeah.
To figure out the moments of the powers of some matrices, or what?
Yeah, I think Aru Bose with the student has done something along those lines. And that was published a couple years after our paper. I think it's in the Annals of Statistics. So he has basically looked at what the free probability limits for these time series are. And I think that the assumptions that he needs are somewhat weaker than the assumptions that we had to put on here.
I just wonder what is the difficulty in applying free probability to this thing? In a sense, like my question, for example, is that in free probability, they are interested usually in the expected value of the normalized trace.
Yeah.
But in this kind of exercises, you're interested in the probability limits of the normalized trace.
Yeah.
So is this bringing the difficulty that it's difficult to go from expected values to probability limits, and like just what is the difficulty?
I think that is primarily the problem. I have to admit that I don't understand enough about this free probability stuff to actually understand where the main issues sit. What I know is that they somehow could reproduce some of the results that we have in our paper under slightly less stringent assumptions. Yeah, but I have to admit that I don't have a good grasp on this free probability stuff. Yeah, and that's probably not a satisfactory answer, but that's yeah.
If you could send me the reference for that.
I'll certainly do that. Yeah.
Thank you. Sorry.
I think the student's name is Bhattacharjee, I believe, and then Aru Bose from ISI. I'll send you the paper. Oops.
So
okay.
Just a very quick question. So this does the MA1 case. Is there? I mean, is it possible to generalize it to higher orders, or is it?
Yeah.
Too difficult?
So we can do it for linear processes, and I'll talk about that in maybe 5 minutes.
Okay.
The reason I do the MA1 case is because it is still kind of intuitive, especially when you talk about how to use Mashenko-Pastur to come up with the time series result. But if I go to a linear process right away, then I think lots of stuff is lost on the intuition. So I should have said this before. It doesn't. Yeah, we did not stop at the MA1. That would be rather limited. Yeah. So just bear with me for just this intuition part on the proof. Thank you. All right. So Gaussianity. Let's assume that one first, and then see what happens. So let's define lag operators and the circulant corresponding. So here you're basically introducing a 0 and you're losing the En in the end. And here you're cycling the En back into the beginning, and the E's are the usual canonical unit vectors. Okay. If I put my data into a matrix X and I do the same thing with the innovations, I can rewrite my MA1 equation in the following form, and I can also just mimic this, and I write a different version that uses, instead of the leg operator, the circulant operator. So x1 is just a redefinition of x, and the only thing that's different is that the first column is z1 plus a1 zn. Okay, so it basically uses the last innovation back there. Okay. However, since L tilde is a circulant matrix, it can be diagonalized in the complex Fourier basis. And we can rotate with this Fourier basis, and we can use that basically the transformation of your Gaussian z's are still Gaussian, so we don't change the distribution. And moreover, if I look at x tilde, which is the rotated version of x1, and then you can see that this rotation basically separates this dependence in a way that now we have coordinates that are all Gaussian and independent of each other. And the transformation, again, respects this MA1 dependence that are sitting there. Okay. So with this little trick, you go from this leg operator, make it slightly different, you make it into a circulant operator, you redefine your process, you rotate in the complex Fourier basis, you're ending up with an independent system. Okay. That's good. Now we can look at the covariance matrix of this transformed data. And we notice that the rank of the difference between S and S tilde is at most 1, because they only differ in one column there. And then we can look at analyzing the Stieltjes transforms of that, so the average trace of the resolvents. And they have the same limiting behavior because they are a low-rank perturbation of one another. Okay, and then after this, and this I don't really want to explain too much about it, but now the random matrix theory apparatus comes into play, and you have to somehow do what Bay and Silverstein do in their appendices in the book, which are basically the most important thing to read in that book are the appendices for those who are interested in learning something about that. Okay, so that is kind of the major trick for the Gaussian case. You can just rotate it and you're going back to the independent case, but that rotated version, which has independent columns, is producing the same spectral behavior as the original one, because we are talking about a low-rank transformation of these things. Okay, to go to the non-Gaussian case, you would basically first apply McDermott's inequality, so show that the expected value is all that it matters because of a concentration. And then, and this is where much of the work is, you show that the difference between these expectations under the Gaussian and the non-Gaussian models is asymptotically going away. And for that, this is a recommended paper, I guess, in general, Saurav Chatterjee's Annals of Probability paper, where he talks about a generalization of the Lindeberg principle that we used here. So that's a very nice paper. Okay, so there's a lot of Taylor expansion arguments and telescoping sums, and you have to bound somehow a certain derivative that come from the Stieltjes transform. So this is, how should I say, maybe a little bit tedious, and you have to crunch through it. The big idea is in the paper of Chatterjee. Once you understand what he did there, you can calculate it for our case. Okay. So of course, then we don't have complex, but we typically have real value data. So you can basically modify this with respect to the real Fourier basis. Okay. Maybe I skipped those details. And now Mashid already asked this question, what about something that's not an MA1? And this is coming here. you could do similar things for an MAQ process, but if we want to do a linear process or MA infinity, because we want to have a causality, AR1 and things like that in the end, so you have to do all of these coefficient matrices, and then this rotation argument won't work because you have infinitely many. So also you need a lot more assumptions on this case. So the first one is kind of to make the theory go through and to make it somehow as well, it is tedious, but as little tedious as possible. So this is not a necessary condition. We have some relaxations in the paper, but I don't want to talk about those here. Maybe more important is that because we're talking about a high-dimensional time series with lots of coefficients, somewhere there needs to be a lower dimensional object that drives the complexity of the time series. And this is done through these continuous functions here. So we have f's that are sitting in a low-dimensional space, and they somehow, by way of this U star ATU mechanism, they do generate the entries of these matrices AT. I'll give you examples of those things, and this typical ARMA processes will fall into this category. Okay, and then again, you need something on regularity of the spectral distributions of these coefficient matrices. All right, so here is just a discussion of the assumptions. You don't have to have this diagonalizability. You can use a certain tuplet structure for the ALs, which decay away from the diagonal at a certain rate, and the same results still hold true. And here's an example how to do an ARMA 1-1 in these assumptions. So that's just the definition of a high dimensional, in this case, or multivariate ARMA process. You have the typical polynomials, and you can basically use the causal representation of this by writing down phi inverse times theta. Okay, if you have simultaneous diagonalizability, then you can basically get two diagonal matrices, lambda phi and lambda theta. And with those, you can look at the coordinates of the then rotated process. And you can see that you write this in one coordinate, you have the lag operator, you expand it in a power series, and then you do a couple of smaller calculations, and you can see that these f functions that will control what is going on in those ARMA matrices, they are given by a few theta and a few phi coefficients, right? So your m is relatively small compared to the p and n that you're trying to send to infinity. So this is kind of the low dimensional structure that would, in the end, hopefully enable estimation of these processes. And this is different from imposing sparsity and sending all kinds of coefficients exactly to zero. All of these can be non-zero, but they are so in a like a low dimensional way through these coefficients. Okay, and then the result for linear processes, Mashid. So this is the same thing, right? So the actual form of the results from MA1 to MA infinity does not change as long as you plug in basically the corresponding spectrum up here, power spectrum, I should say. So the situation, the integrals don't change. Of course, solving them will be more complex, but the general form remains intact. Okay. All right, so the examples out of this, if all the ATs are equal to 0 and you have no time series, so the spectrum is equal to 1, then you're getting Mashenko posture back from that, in which case these integral equations that they can be explicitly solved, and you're getting those densities back that we saw earlier on. That's unfortunately not possible in the general case. If you talk about row-wise independence, then you can run your AT matrices as copies of alpha t times the identity. You plug it in, and then you're getting the Stieltjes transform that Pfaffel, Schlemm, and Yao derived in their papers. And you could do causal AMA processes by determining the causal coefficient in the causal representation. Okay.
Alex, can you get rid of simultaneous diagonalizability to some extent?
Yes, you can if you're assuming this triplet structure. So something that is still like kind of diagonally dominant, but it has.
Yeah, suppose that you have moving average, I don't know, of order 2. But instead of considering the data like each time period, you are kind of just considering it every second time period. So you effectively kill the dimensionality there. And can you say something about like the sample covariance like of the original series from that?
So you would go from P to 2P, right?
In for example, no.
Yeah, I think that would actually work as long as you have a way to kill the dependence in that way. So certainly for MAs, it would work. Of course, if you have a long time series, then your P could get a long dependence. Then the multiple of P that you have to take could basically kill the gains, right? So in a way, when.
But I guess in many applications, people worry about temporal dependence, but they are happy to assume quite fast decaying dependence. So
I guess you still have to control the remainder, right? If you're basically saying that your time series is well approximated by an MA of order M. You have like some sort of an M-dependent process that you say is a good description of the actual dependence. Then you would go to an MP dimensional process, and you could apply MP law directly. However, there's still the remainder, right? So you have to make sure that whatever happens in the tail, it doesn't destroy this, and probably it will need some conditions somewhere.
Okay.
Yeah, I don't know which ones, but yeah.
We've got about 15 minutes left.
Okay, so yeah, I'll try to go quicker, I guess. Final comments on the proof. So let's see, the arguments that we've made so far won't work because again, this transformed matrix is changed everywhere, and it doesn't only affect like the first few or the first column, like in the MA1 case. But you have a way of going around this, and maybe this is kind of what Alexei had in mind for the MA approximations too, because something like that happens here. You're basically going to a finite order MA process. You cut it off at a certain level, but you want to have Q of P go to infinity, but not too fast. And if you look into the calculation, P to the 1/4 is actually the right order to do that. So if this would still be P to the 1/4, if we're doing Alexei's idea, I am not sure. It could work. Okay, so symmetrized autocovariance matrices. Again, we didn't do the actual ones because we want to have at least real eigenvalues. So what we're looking at is the Lec-tau symmetrized sample autocovariance. And we can define correspondingly the tau empirical spectral distribution down here. And then when you try to look at the CT tilde version of the same like rotated version, then you see that you're adding this cosine term in there. Okay, and otherwise now the result for that becomes the same, and the only thing that's different from before is that the cosine term comes in. If you're at tau equals 0, then the cosine term is 1, and you basically have the old results again. Okay, that's what it says there. Maybe I go a little bit faster on the discussion of the results, so I can still say something about hopefully the last time. I can still say something about this, the mean variance frontier kind of thing. So the first thing that I want to say is one of the problems where whatever we found our results could be useful is signal detection, because we kind of have the histogram of what is expected in the time series case rather than the histogram of what is given in the independent case. And for that, you can think about problems of detecting low-dimensional signals in high-dimensional noise. You can talk about diagnostic tools for high-dimensional time series using these ESDs for autocovariance matrices of different orders. That's something that Jin et al. Already had kind of thought about in their paper, but they had only results for the independent case. And it can just be a general tool to guide on the nature of the dependence in the observations. Okay, and a couple of other things. And then I have a couple of potential applications. Alexei has, of course, worked on these dynamic factor models as well. I can maybe skip this, and Alexei can ask me difficult questions after the talk. And I go to the summary of this part B. So this older paper gives us some ideas about how Marchenko-Pastur would work for time series under certain perhaps restrictive assumptions. There is some potential for applications, and we're going to talk about one of those that we worked out in more detail, the mean variance frontier estimation next. But I should also say that there is certainly a lot more work needed to estimate coefficient matrices, to understand actually what the limiting ESD looks like. So far, these are just these integral equations, but it doesn't say anything about properties of that limiting ESD. And then all kinds of other downstream problems that could be talked about and that we haven't done anything on in the last few years. So, yeah. All right, so let's go to estimating quadratic forms for these time series in about 5 fast minutes, I guess. So the goal is we would like to see this more applicable. And so the problem we figured out where it would be useful is something like quadratic forms of the sample covariance matrix. And one of the examples where that shows up is a Markowitz portfolio problem and then the mean variance frontier. The issue is that you have a certain true frontier and you get a sample frontier that basically looks a lot less risky than the truth would be. And we're trying to use the previous results together with thresholding and model selection procedure to set this up. Okay, so the background is the following. We want to assemble a risky portfolio of assets V1 up to Vp. These assets have certain expected returns, mu, and they are interrelated through a covariance matrix, sigma. And we would like to say something about mu capital P, which is the expected portfolio return. And we would like to choose an allocation that minimizes the risk that we're exposed to. Okay. As a mathematical problem, this becomes a quadratic program. So you have to solve this minimization problem. There are a couple of constraints in there. And then if W opt, these are the optimal weights, then this thing viewed as a function of the expected portfolio return is called efficient frontier. And then if sigma is an invertible matrix, then you can have an explicit form for those optimal weights. Okay, So common practice is use the expected return vector mu and use S in place of sigma. And when N and P are comparable, this has been leading to this risk underestimation that people have certainly recognized in practice. In the high dimensional setting, there are results for independent observations. Nuruddin El-Karoui has done something on that a while ago, but not when the observations themselves are considered time series. And this is where this work comes in. So if you have a quadratic form Q involving the covariance matrix, you can certainly set up the same thing with Q. Sometimes you have to estimate that matrix V, sometimes not. But what we know is that certainly these Q estimates here, they will be biased. In the Markowitz portfolio problem, we can see that you can define the V's in a certain way, and it becomes subsumed under this more general problem of estimating quadratic forms. Okay. So let's look at where the risk underestimation actually comes from, and then after that I'll just show you a couple of pictures and I'll let you go. So there's two different weights. There's the optimal weights that are calculated from the quadratic program using the population quantities, and then there is the solution of weights that come from the sample problem. That's right there. And then just assuming P less than N for simplicity, you can look at these differences, right? So this is what the quadratic form involving the sample covariance matrix looks like. So the whole thing is not exactly proportional to what the population version is, but it is proportional only to the standardized version. So you have to basically debias it with this term D down here, and you have to scale it with a term that basically adjusts for degrees of freedom, kind of, that is here. But what you see is that this will always be often much smaller than what the actual quadratic form value is like. And so that explains in an intuitive way where this difference that you observe in practice is coming from. And once you understand where it's coming from, you can try to remedy the situation. And maybe I skip through this algorithm here, so we can do all kinds of things, but maybe to just give you the gist, here is what happens in empirical situations. So the green one here is the true risk. This is based on an MA2 process, which has 1,000 coordinates, and we have 3,000 observations of that. Then there is the naive estimate in there, which just uses the sample covariance matrix. And then you can see that this leads to this risk underestimation in that case. Int shrink is a certain shrinkage estimation proposed by Nuruddin El-Karoui. And you can see that this corrects much of what's going on, but it still stays away from the true green one. And if you do this, the proposed method that uses kind of the time series dependence, it does not know, and this is why it says model selection, the proposed method does not know it is actually an MA2 process. It just figures out somehow from the data what kind of MA process to use. And if you do that, then the green and the blue, so the truth and the mean of whatever you do in the model selection, they match up kind of okay in this case. And you can do similar things using an AR1. So here the aspect ratio is a quarter. The labeling is as before, but we're talking about the situation that the model is misspecified, right? And AR1 is an MA infinity process, but we're approximating it by an MA2 process, for example. So it's not necessarily MA2, but I just wrote it there. So if you do this, then the situation is a little bit more complex. The proposed method is still kind of closest to the green frontier, but it's not spot on anymore. So there's still some scope for more work on that. And with this, I think the hour is over. I would wrap up. So I tried to talk about the bulk eigenvalues of sample mostly covariance matrices that come from MA or more general linear processes. I think there is a lot of difficulty in finding the appropriate models for these high-dimensional time series. There's certainly scope to relax assumptions, but I still believe that there is some potential for this to work in applications, and one such example is this mean variance frontier that kind of was getting a little bit short notice here in the end. But certainly there's a lot more that could be done, and I'm not sure I will do it because I kind of got old and slow in the last 5 years. Anyway, with this, I would like to say thank you for your attention, and I look forward to the question and the discussion.
Well, thank you so much, Alex, for a wonderful talk. So the floor is open. Anybody who has a question, please go ahead. I'll turn their